This is Chapter 9, Part 2. So, when we're talking about microbial control and sterilization and considerations in relation to those things, we have to think about what the substances are: durable solids such as rubber to sensitive liquids like serum. Um, there's no universal methods to that we can use because some instruments are fragile and can melt in the heat. So it just kind of depends on what we're trying to sterilize. Other considerations are cost, the effectiveness of the sterilization, and then the method of disposal. So something like blood or body fluids, we have to have a specific protocol set up in order to dispose of those things even after sterilization. All right, so what is microbial death? So death is the permanent termination of an organism's vital processes. That is the definition of death, or in this case, we're talking about microbial death. So it cannot reproduce, it cannot do its normal stuff. Microbes have no conspicuous vital processes, therefore, death is difficult to determine. Permanent loss of reproductive capability, even under optimum growth conditions, has become the accepted microbiological definition of death. So, right here, permanent loss of reproductive capability for microbes, right, like bacteria and such. Factors that affect the death rate. So death of a whole population is not instantaneous. Begins with a certain threshold of microbicidal agent is met. Death continues in a logarithmic manner as the time or concentration is increased. Active cells tend to die more quickly than less metabolically active cells. I don't know why I can't talk today. And eventually a point is reached at which survival of any cell is highly unlikely. This point is equivalent to sterilization. So factors that influence the action of certain antimicrobial agents, such as, 5% bleach or 10% bleach or whatever. So it depends on how many microbes are present. There's a higher load of contaminants, then it takes longer to destroy. The nature of the microorganisms in the population. If the target population is a mixture of bacteria, fungi, spores, and viruses, that will give them a broad spectrum of resistance. In addition, the temperature and pH of the environment. All of these are things that influence the agents that we use to essentially get rid of or kill a particular type of microbe or sterilize a particular device. All right, more on this. The concentration or dose or intensity of the agent. So, an agent, I mean, like, whatever you're using to either decontaminate or sterilize the device or whatever. So UV radiation is most effective at 260 nanometers. Most disinfectants are more active at higher concentrations, and that kind of makes sense. It's kind of something that seems logical. In addition, we have to consider the mode of action of the agent. So how specifically does it kill or inhibit the microorganism? And then also we need to consider the presence of interfering organic matter and inhibitors. So things like saliva and blood and feces can inhibit the actions of disinfectants and even of the heat. And to clarify that, just like disinfectants have a certain way of getting done what we need to get done, heat can be affected by things like saliva, blood, and feces, and how effective heat can actually do its job. So antimicrobials have a range of cellular targets. There's least selective agents tend to be effective against a wide range of microbes. So if it's not very selective, it's like a great big, broad spectrum type of thing. Then they're going to be effective on a lot of different microbes. Examples would be heat and radiation. More selective agents target only a single cellular component, such as a drug. So drugs are known to be a little bit more selective than things like heat and radiation. Cellular targets of physical and chemical agents include the cell wall, cytoplasmic membrane, cellular synthetic processes, so processes making the DNA or the RNA, as well as proteins. So actions of various physical and chemical agents upon the cell. This is a quick reference. I would read through this once just so you know what is on here. Mode of action of surfactants on the cytoplasmic membrane. I just left this in here, so as you're reading through, you'll be able to reference this. It's not something, I'm not going to test you on this picture in any way. So COVID-19, alcohol-based sanitizers are the mainstay, the go-to type of disinfection of surfaces and antisepsis of the hands during this pandemic. There's a time where, they're rationing Purell and other hand sanitizers, and I think most of us have figured out fairly quickly that not all hand sanitizers are created equal, and that there are some good ones out there and some not so good ones. Germex and Purell seem to be my go-to ones that don't make me feel sticky after I use them. But SARS-CoV-2, COVID-19 is an enveloped virus. As you know, hopefully you'll know what an enveloped virus is by the time we get to this chapter. And its envelope itself is susceptible to both detergents and alcohol. So that's why they recommended so much that we were using these hand sanitizers to take care of our hands when we weren't able to wash them. All right, and just on a side note, I've always kept hand sanitizers in my car, hand wipes when we go on trips and such. So this is really, I didn't have to do too much different with how I handled the outside world other than the mask stuff, because I know enough that I knew that I didn't want to touch the door handles on the bathroom stalls because not everybody handles things the same way, we'll say, and so I just don't trust that people wash their hands the way they should, and so hand sanitizers are, even if I wash my hands in the bathroom, when I get out to the car, I always go ahead and use some hand sanitizer, and that's just how I've always been, and it's worked for me, as far as warding off some of the illnesses that have gone around over the years. So methods of physical control: heat. So elevated temperatures are microbicidal. We know what that means now. Lower temperatures, such as refrigeration, are microbistatic. So moist heat, hot water, boiling water, or steam between 60 and 135 degrees Celsius are considered, more effective than other types. But we'll get into that here shortly. Dry heat, hot air or open flame, is also fairly effective, but again, only certain things can withstand these two things. Moist heat operates at a lower temperature and shorter exposure times to achieve the same effectiveness as dry heat. So think about that. So moist heat works better. It can go at a lower temperature and a shorter exposure time to achieve the same effectiveness as dry heat. So microbicidal effects is the coagulation and denaturation of the proteins in those cells. Dry heat dehydrates the cell, removes the water that's necessary for metabolic reactions. Sometimes it turns them to ashes. It depends on what we're using. It depends on the temperature. This is just an illustration or a diagram of what we're talking about here. What would happen if this is the native state? We know what a native state of a protein is. If we, completely denature it, then it's going to no longer be that perfect, in this particular case, enzyme, and it's not going to work right, right? Depending on what we do, it can actually change the shape enough where the substrate cannot connect anymore. And if we change the shape enough, these agents will block the substrates from attaching to the actual enzyme. So the agents that we use kind of can mimic the action of these of the original substrates. All right, so temperatures to achieve sterilization with moist and dry heat. So moist heat, 121 degrees Celsius for 15 minutes, and pressure helps with that. Dry heat, 121 degrees Celsius for 600 minutes. So you can imagine this moist heat thing works way better. You're not going to have to regurgitate this to me necessarily, but I am going to ask you about sterilization. And later we're going to talk about that through sterilization through autoclave techniques, and it would be 121 degrees Celsius, 15 minutes with, I think it's 15 psi, but we'll talk about that later. So I am going to stop here and pick up on part 3.